It's always a pleasure to come to Santa Cruz. I understand that we are running a bit late, and I'm the only thing standing between you and lunch. And I'm afraid that the only appetizer I can offer is Starburst. Many flavors, but Starburst. I'm not the only one to blame. I'm also blaming my collaborators. They are cowardly, hiding at home, except Oscar Gertz here at the back. And so I'm gonna tell you a bit more about this project that we've been doing about the last years on this Starburst activity. But first, I would like to start with kind of a rant on vocabulary, differences between efficiency and efficiency. If you talk to large-scale people, galactic-scale people, like most of you are, large-scale star formation efficiency means basically the ratio between star formation rate and the mass of gas, which gives you an inverse of time. Basically, that tells you, for given gas mass, how fast star formation is. If you talk to smaller scale people, or if you are putting this information into a subgrid recipe for your simulations, then your star formation efficiency at small scale is the ratio of masses, the ratio between the stellar mass and the mass of your, for example, star forming region of a cloud, for example. That means it's dimensionless. And that tells you that for a given gas mass, how much stellar mass is formed. Clearly, these two quantities are not the same, and it's actually very difficult to try to connect them together over a range of galaxies. But now, if you go back to the generic definition of what an efficiency is, it's how much you get out from what you put in, which implies it has to be a dimensionless quantity, which means that this is not a star formation efficiency. That doesn't mean that there is no information in this quantity, but maybe we should rename it. And there is already a way to do that, which is just to use the depletion time, just inverse, ratio between the mass of gas and your star formation rate that gives you a time. It's even simpler, equally useful, and without the confusion. So I would encourage everybody to use that. Instead, that means exactly the same, but no confusion. This being said, the main question I want to address today is what makes a starburst starburst. I think the best way to illustrate that is to go to Schmidt-Kennicott plane, surface density of gas versus surface density of star formation rate. You have a power law relation, deviations, breaks, debated index, etc. Let's forget about all that for the moment, and let's consider a galaxy on this star forming relation there. Now, for some reason, this galaxy will go into a starburst episode. So what can it do? A boost of star formation activity could be due to several factors. One of them is increased mass of dense gas. If this happens, then more stars are formed per unique time, and you move along this power law regime. You can also have an increased star formation efficiency, the small one, the small scale one, ratio of masses. If this happens, that means that more stars are formed per unit mass, and then you go up like that. And you can also have the increase of the other efficiency, so decrease of depletion time, which means that stars are formed faster per unit mass. And this would go in that direction. Of course, it could be also a combination of all the above in different ways, and probably varying in time and in space and from galaxy to galaxies. So can we try to learn a bit more about that? Well, from the observation, it's not so easy. Here you see entire galaxies or regions in galaxies are disk galaxies, dilated disk, at low redshift and high redshift. High redshift here means 1 to 2, basically. And you see that these are lined up on the Kennicott-Schmidt relation. Not to be confused with the depletion time, because here you have a superlinear power law. So depletion time, line of constant depletion time would be something like that. And for this type of galaxies, it's usually between 1 and 10 billion years. Now, if you look to starburst galaxies, do they have a reduced depletion time? The observation would place them here. So in the LURGS and ULURGS, ultra-luminous infrared galaxies. And that would mean a reduced depletion time by a factor between 10 to 100 with respect to the elevated disk. But there is a caveat here and a big problem, which is you don't exactly know what is your mass of gas here, because you observe the CO luminosity. So there have been uncertainties on the conversion factor between these two quantities through either XCO or alpha CO, as you prefer to use it. And this factor is quite big, so you can move these points back to here, and that they could lie down on the regime of disks. So you could actually question the existence of this starburst regime, or at least see an influence of the slope of the Kinnear-Schmidt relation. So can we try to help observers with this from a theoretical and numerical point of view? Well, we can try. So let me go back to the basics to make sure that everybody is talking, we are all on the same page. I consider a volume of gas of mass m. I have an average density here, and I can normalize my actual density of gas by this average. And it turns out that the distribution of gas densities, so the PDF, has a log normal shape in supersonic isothermal turbulence. So you have a little twist here, which you have a plus sign for volume weighted gas density PDF, so if you're counting your cells or your pixels, and you have a minus sign if you have a mass weighted. It's very easy to convert one into the other. And indeed, when you observe this distribution of densities at cloud scale, for example, you see this kind of log normal behavior, plus this power law tail, which is the onset of self-gravity. So now if you go to a simulation of galaxies, most of the time we don't reach such high resolutions. We are stuck at around parsec resolution now. Like in this example by Kern-Grisdale, you see here the example of 3 different PDFs for different galactic type. And you don't see the power law regime here. We don't resolve that. We don't capture the gas dense and cold enough to have this power law tail. So of course, we also have artifacts at the very high density at the end of your distribution, which is due to limited resolutions, basically the gas piling up in your last density bin in your galaxy. But something that we get better than simulation of clouds, for example, is that we have information about what is around the galaxy, the CGM, and the low density part. Of course, as we have heard before in the week, and this is very complicated to model and to understand. And Eric Anderson is keep worrying me by the effect of runaway stars making a big difference in that. And of course, in this type of simulation, the other big effect that you're missing is the rest of the universe. So that's why now we are considering cosmological volumes, as this is not running. Okay. So this happens if I trim the movie. Okay, so the movie is actually 2 minutes long, so that's why I try to trim it a bit. I'm very pleased to introduce the Vintergatan simulation. Vintergatan is Swedish from the Winter Street, which actually means the Milky Way. And as you can see here, it's a zoom-in simulation for the formation of the Milky Way. Unfortunately, I don't have time to give you more details. I was just super excited to show you this because we basically decided on the name yesterday. So we are following the formation of Milky Way through the assembly, the equation, the major mergers. We are making fancy images like that. And you will hear much more about that in a few weeks. But using this simulation, I can really look at the properties of the interstellar medium. And this is just a snapshot at a random redshift, totally random, 6.1. And this is what the Milky Way looks like at this redshift. So if I zoom in a bit, this is our galaxy or home soon. And you see another galaxy passing by. So I can measure the gas density PDF again, doing that, and this is what I get. So of course, it's very tempting to fit a power law, and you are very disappointing because of these big deviations here and there. So maybe the reason why it's not working so well is that maybe you can see that you have a split around this density here. So what I did is to try again to fit 2 halves of this distribution like this. Of course, you improve the quality of the fit, but it makes not much sense to fit them with the same average density because you're actually probing 2 different phases in your galaxy. So instead, I let the average density to be a free parameter and do a fit again, and I get a much, much, much better results like this. So now because we have some constraint on the circumgalactic medium, I can, for example, decide kind of arbitrarily that this part at low density is my reference, and then I can then conclude that I have an excess of dense gas at these high densities. Why is that? Well, the culprit is just here. This galaxy will merge eventually with the Milky Way within a few 100 million years. But just before it passed by, tickled it a bit, and created all this excess of dense gas. How do I know? Well, in cosmological simulation, it's a bit difficult to see that because you don't have full control, you don't have very comfortable resolution to do that. But luckily, I have my old simulation of the antenna galaxies. So you see two galaxies here interacting and merging. In the process, they form a lot of massive star clusters. And with 1 parsec resolution, I can actually measure the gas density PDF with much better confidence. And this is what I get. Before the interaction, we have a nice log-normal shape like this. And during the interaction, that's what we have. So once again, I will not trust too much the last beams over there, but you see that over several decks, I have a strong deviation with an excess of dense gas. Here I want to stress something very important, I think, is that it's not a shift of your log-normal. It's not a widening of your log-normal. It's not log-normal shape anymore. You change the shape of your distribution of gas. Why does it matter? Because this gas is basically the ingredient for your star formation recipe. And then you will put this distribution in this superlinear model or any other flavor that you prefer to form your stars in your galaxy. So if I go back to this little cartoon I had and I compare what happened if I have a log-normal distribution versus an excess of dense gas like this one, in log-normal case, I can put, for example, more gas with the same log-normal distribution. That's what I would do if I go to a high redshift isolated galaxy. And then I will move along the disk regime like that. Now, if I do an excess of dense gas like this, for example, in mergers, I get to a different regime. I have a discontinuity in the evolution of the galaxy. And I'm not in the canonical Kinecott-Schmidt regime anymore, which means that I move up somewhere. We don't know exactly where. So let's have a look at the simulation to try to understand better what's going on and what's behind that. So we do see differences in depletion time in observations. This is a pair of galaxies, and you see in different pointings, you have almost 2 decks difference in the depletion time. Same in this one, you almost see gradient. Again, 2 decks for these galaxies interacting with the very dense intergalactic medium and the elliptical one here. And of course, we did the same with the antenna simulation, and here it is. So you see at the instance which best matches the observation. It's not perfect, but it's not really the point. You see almost also 2 decks of scatter in depletion time. So the obvious thing to do was to look at the reason behind that. So I looked at the usual culprit. I show here just a few, the shear, Mach number, compressive turbulence, everything that could affect star formation in a positive or negative manner. Well, star formation sites that don't really coincide with this usual suspect, and trust me, I trust many others. And at some point, I understand why. It's because in this kind of merger, you are basically in a cosmic blender. And your dynamical timescale is very short, something like 10 million years, which means much shorter than the time it takes to assemble a cloud, make the cloud collapse, fragment, and form stars. So in other words, once you see star formation, or when you see young stars in observation, the effect, the trigger that created this event might be long gone. Could be on the other side of the galaxy, or could have been disappeared. Of course, you could say, well, that's bad, but we can correct for this by correcting with the timescale effect. No, you can't, because you have a diversity of timescale due to a diversity of processes acting in these galaxies. You have shocks, you have tides, you have inflows, maybe something else. And of course, you have variations of these processes and their combination across space and across time in different stages of your interaction. So does it mean that we are stuck? Well, maybe not. Let's go to smaller scales, and let's look at the Schmidt-Kinecott diagram again, but this time on a cloud-by-cloud basis. So I used to plot a line of constant depletion time. You have to imagine it. And here, so it's happened to be 40 million years. I'm still not quite sure why it's 40, but whatever. And I look at all the clouds in the simulation of the antenna galaxies, and this is what I get. You see different colors and shape of the point for different regions in galaxies. Basically, there is no information there. The 2 outliers up there are the galactic nuclei. You can put them in your analysis or not. It makes no difference at all. And what you see here is basically a break in this region. It's not really a change of your power law slope. It's not true regime. It's just this weird transition there. So what I did next was to identify the clouds below this constant depletion time regime, below this kind of transition. So long depletion time, or if you're old-fashioned, not efficient at forming stars. And then I stacked their gas density PDF. And this is what I got. So it's not perfect log normal, but it's clearly a bell shape like that. And I did the same for the clouds forming star efficiently or with short depletion times. And this is what I got. And clearly, we have an excess of dense gas here. So that means that short depletion times up there means excess of dense gas and deviation from this log normal PDF. Now, how can we translate this back into large scales? Well, it's not so easy, but maybe if we go to the time dimension, that will make a bit more sense. So here I'm showing you now the evolution in time of the entire system of the antennae galaxies that we model. Just to get your eyes, I have the regime of disk here, the regime of starbursts up there. We start just below the regime of disk here in isolation. And now I will plot the evolution. Between two dots, you will have 10 million years. First collisions, you jump up there. Then it's a bit of mess in this blender. And then second collisions put you there. And final coalescence. So we had to stop the simulation because it's quite expensive, but I know that with lower resolution models, you'll come back to the regime of disk within a few 100 million years. So the point I want to make here is that you have here 3 starburst episodes. First passage, second passage, and coalescence. And they have completely different signature in this plot. They are not parallel, they are not similar or anything. And the reason for that, I think, is that if you analyze the known triggers, the physics behind starburst activity, you basically have 3 main factors. The first is nuclear inflows. That is the strongest just before coalescence when you have strong tidal torques. The second one would be shocks, including cloud-cloud collisions when the 2 galaxies are penetrating. So quite late also. You need to lose a bit of orbital angular momentum through dynamical friction to reach this point. And the third one is the tidal and turbulence compression, and because it's from tidal origin, it's a remote effect, and it's affecting large volumes and quite early already in the interaction. So of course, if you have different combination of these 3 factors at different stages during your merger, and also at different positions, so combination of space and time, then you will get these many flavors of starbursts that are illustrated in a complicated way in here. So now it would be really nice to see if we can distinguish them observationally. And I think we can. So to reach this conclusion, what we did is to use a large velocity gradient method, LVG, and to apply that to a bunch of simulations. So here I'm showing you the 2 flavors of the SLED, spectral line energy distribution. This one is flux integral, this one is integrated density. You look at the one you like, and you don't tell me why it's better than the other, please. What I'm showing here is 3 simulations of reference. So a Eulerg phase, so quite intense star formation activity, and then 2 isolated disks, one at high redshift here and the Milky Way there. And you see that the 2 disks have a closer distribution regardless of the star formation rate. Now what I'm going to do is to pinpoint different regimes, different regions in the antennae simulations. To make it a bit clearer to follow, I will just tell you where they are in the real system, but we, of course, use the simulation. So let's start with this region, which is the northern nucleus. And you have this kind of distribution, quite close to the Eulerg regime. Southern nucleus, not much of a difference. The overlap region, when the 2 galaxies actually overlap here, it's kind of similar. But don't forget the 4th very active region in the antennae galaxies, which is here, the arc, when you form a lot of massive clusters also. And you see a bit more differences. I think it's clearer on this plot with integrated density. Here you see a deviation here in your spectral line energy distribution. And this could be a different signature of a different physical trigger that we have to explain the star formation activity. So the main difference is, I think I found at high J, high transition level, which means that corresponds to the warm gas, and I think it's due to a different efficiency in propagating the feedback. So basically, based on the porosity of your interstellar medium, which is different in this region and in this region, for example. Now, if I go back to the global scale of the entire galaxy, this is what I get. And you see it's not really matching well any of the region. It makes sense. It's just a mix of all the star-forming regions and also other in-between regions which are a bit quieter, less excited interstellar medium. So how much time do you have left? 3 minutes. OK, so using this simulation and this same large velocity gradient method, we have been able to maybe help the observers in this big task of choosing this alpha CO conversion factor. So what we do is using, again, the same set of simulation, plotting the alpha CO that we derive from the simulation versus star formation rate. We start with the Milky Way-like galaxy with the, I would say, normal canonical alpha CO value here. We also have a high redshift disk, clumpy disk. And we have the two galaxies that make the progenitor of the antennae run in isolation. So here you see at different epochs. I think the difference is because one of them is forming a strong bar. And now what I'm going to plot is the evolution of the antenna galaxy itself, the merger, in this plane. But because it's going to be a bit messy, I will try to make it clearer by showing the evolution of the two quantities, so star formation rate and alpha CO, as function of time. You will see the color codes the time, and you will see it's a mess. So we started there in the regime of the progenitors. And then we jump during a starburst. We try to go up, and then second starburst. And we try to go up a bit again. And one more time, we had to stop the simulation here. So it's very frustrating because I would love to see this coming back up there. But I don't know. I think it makes sense, but it's not in the simulation, unfortunately. So what we can see from that is basically that we have a regime of disks. So for the isolated disk, obviously, and also for the merger itself before the peak of the first starburst, including during the rise here, because the feedback effect has not time to propagate to affect the excitation of your gas there. Then you have the regime of starburst during the first and second peaks, basically first passage and second passage plus final coalescence. And in between, you have this regime where the galaxy tries to go back to isolated regime, which I call a post-starburst. So this means that alpha CO is clearly not based on star formation rate alone. You have a huge degeneracy between these two regimes, for example, but much more on the phase of the interaction of your galaxies. So just as a side note, you can see that the very low values that have been used before in the literature can be reached if you go to very high star formation rates, so basically here. So if you're in lurgs or U-lurg phase, it's actually OK to use values as low as 0.8, etc. Which validates the choice of, that has been made before, and that validates also the observational proof of the starburst regime in a Kinecke-Schmidt plane. So now it's time to reach my conclusions. I've told you today that the SFE is not an efficiency. Please consider that it's very confusing to have two star formation efficiencies, and instead please use the depletion time. It's just the inverse of your SFE that you like. It's exactly the same. I've told you that starburst is both an increase of the dense gas mass and a decrease of depletion time. It's visible as an excess of dense gas, which is induced by turbulence compression. And this effect, which effect between the increase of dense gas and decrease of depletion time dominates, varies a lot in space and in time. You can consider different regions in one galaxy or different phases in their interaction. The underlying physical trigger of a starburst can be identified using the CO spectral line energy distributions. And finally, the alpha CO factor evolved along the three regimes, the disk, the starburst, and the pulse burst. So if you have access to information on the morphology of your merger and then on the star formation rate, then I can tell you which value of alpha CO you should use to get the mass of gas in your galaxy. And the last point is that Wintergatan is coming. Thank you very much.
Okay, after questions, we're going to have one announcement, but now questions.
So this is really nice. The alpha CO factor is function of star formation rate. If you would go into your simulation of a disk and you zoom in on one particular star formation region, does that look like a starburst? In other words, can I think of a disk as a collection of individual little starbursts combined with basically a bunch of non-star forming gas? Does that work, or is that?
Yes, I would say yes. The problem is that you need very, very high resolution to look at individual regions. So we did that. It's very noisy. But it's compatible with what you said. And from the spectral energy distribution, that's exactly what you said.
Hi, Florent. Yeah, this is really interesting. I'm just wondering about, so your PDFs, I'm wondering about how you sample the ISM for those, like specifically the shape and things like that, and if the PDFs are robust to different ways of doing that.
Okay, so I sampled them over the entire galaxy. I ignore a bit of the intergalactic medium.
But what shape do you, like, do you do spheres?
Oh,
or?
it's sphere, it's cube, it's a cylinder. It makes no difference.
Okay.
You will have some difference in the very low part of
Yeah.
the low density things, but I'm not saying anything about that.
Okay.
So that's as long as you have a representative part of basically your star forming gas, then what I say holds.
Great.
Last question.
You said that the starburst is an increase in gas mass and a decrease in depletion time.
Yes.
But when you move up above the main sequence, that's exactly what happens. For all galaxies above the main sequence, depletion time is shorter, gas fraction is higher. Do you then argue that all of these galaxies are in starburst mode?
No, I will not go that far because that's the reverse argument. What I'm saying is that starbursts do that. I'm not saying that if you do that, you are a starburst.
Ah, you sneak out.
Yes. I think you have to look at indicator of star formation history then to conclude.
Okay, so let's thank the speaker again. And now we have an announcement.